Part 5. Determination of the concentrations of H3O plus and anions of a polyprotic acid. So let's say that we would like to determine the concentration of H3O plus ions that a polyprotic acid produces. So how would we be able to do that? Well, here I'll show you an example problem to show you how we can determine the concentration of H3O plus ions that a polyprotic acid produces when it is dissolved in water. Let's say we have 4 molar of H3PO4, otherwise known as phosphoric acid, that dissolves in water. The Ka1 for this acid is 7.2 times 10 to the negative third. The Ka2 is 6.3 times 10 to the negative eighth. And the Ka3 is 7.1 times 10 to the negative 13th. And we would like to calculate the concentration of H3O plus in this solution. Well, first, again, like with any of these problems, we have to understand what is happening when H3PO4 dissolves in water. Now, we know from the previous part that there are 3 reactions that actually happen. Each time the H3PO4 loses an H, so to the water, and makes H3O plus, and then it makes H2PO4 minus, which then again loses an H, that makes another H3O plus, and that yields another HPO4 minus, since this H2PO4 minus lost an H to make HPO4 minus, and then the HPO4 minus loses another H to water to make another H3O plus, and finally we're left with the PO4 minus. And each of these reactions has a different Ka. There's a Ka1, Ka2, Ka3. And these Kas progressively decrease in their magnitude as we go from reaction 1 to reaction 2 to reaction 3. We also have to notice that the Ka1 is much greater than the Ka2 and the Ka3. In fact, as you can see here, the Ka1 is 5 orders of magnitude greater than the Ka2, and the Ka2 is another 5 orders of magnitude greater than the Ka3. So essentially the Ka1 is much greater than Ka2 and Ka3. You see, the 7.2 times 10 to the negative 3 is much greater than these two other values. It's so much greater. And that basically means that this reaction happens to a much greater extent, than these other two lower reactions. So although each of these reactions contribute H3O plus to the solution, we should probably only care about this first reaction, because it produces the most H3O plus. In fact, it produces so much H3O plus relative to these other two reactions that the H3O plus that is produced by these other two reactions is essentially negligible, because their Kas are so tiny relative to this first Ka1 that basically, even if we do find the H3O plus concentrations produced by these, they don't really matter. They're not really going to change the overall value of H3O plus produced, because this value of H3O plus produced is so much larger than these other H3O pluses. Their addition is not going to make much of a difference. So if we know that only this first reaction really matters, then this problem becomes a very simple problem, because we only need to find the H3O plus concentration produced for this reaction. And then it becomes like a simple acid dissociation problem. First, we'll have to draw the equilibrium equation for this first equation, and that will be Ka1 equals the products multiplied by each other, the concentrations of them, so H3O plus times H2PO4 minus, over the concentration of the reactants, so H3PO4, and we ignore the water, as always. Now we just plug in the values, so 7.2 times 10 to the negative third is the value of Ka1, and that will equal to the initial concentration of the H3PO4, which is 4 molar, minus X. And for every X of this acid that's dissociated, an X amount of H3O plus gets produced and an X amount of H2PO4 minus gets produced. However, due to our small number assumption, the approximation, we know that the 7.2 times 10 to the negative third is more, actually the 4 molar initial concentration of the H3PO4 is more than 100 times greater than the 7.2 times 10 to the negative third Ka value for this. Therefore, we can ignore this minus x on the bottom and take it out, and our equation becomes 7.2 times 10 to the negative third equals x squared over 4. Now we just multiply this 4 by 7.2 times 10 to the negative third. We get 0.0288 equals the x squared. Take the square root of the 0.0288 and we get 0.1697, around that to 0.170 molar of H3O plus. So the concentration of H3O plus is essentially 0.170 molar for the 4 molar of this phosphoric acid that was dissolved in water. However, things become a little bit more tricky if, let's say, the exam asks us to find the concentration of one of these anions. So this H2PO4 minus or HPO42 minus or PO43 minus. And see, there are plenty of anions that the exam could ask about, and it can ask to find the concentration of HPO42 minus or PO43 minus, and we need to know how to find the concentrations of these anions. So in this case, let's say that the exam asks us to find the concentration of PO43 minus, and I'll give you an example problem showing how to find that concentration. So to illustrate how to find the concentration of PO43 minus, I'll use our previous problem with the phosphoric acid. In this problem we have 4 molar of phosphoric acid, H3PO4, dissolved in water. Here are the different Kas to K1, K2, and K3 of phosphoric acid, and we need to find the concentration of PO43 minus ions in the solution. So again, we have to understand what is happening when the H3PO4 is dissolved in the water. So we have our reactions for the polyprotic acid. And in this case, we unfortunately, unlike in the previous problem, we cannot ignore these second and third reactions, because the PO43 minus concentration is yielded only by the third reaction. So we have to work with all three in this problem. So since the third one is the most important one in this case because it produces the PO43 minus, let's start off by drawing the equilibrium equation for this third reaction. So the Ka3 equals the products multiplied by each other, the H3O plus times the PO43 minus concentrations, over the reactants, the HPO42 minus, again ignore the water. And then we plug in what we know for these concentrations. At least we know some of the initials. From the previous problem, we know that most of the H3O plus, or at least the concentration of H3O plus that matters, is only produced by the first reaction, because Ka1 is so much larger than the K2 and K3 that these two other ones don't really matter when influencing the concentration of H3O plus. So essentially we can use the H3O plus concentration we calculated from the first problem and plug it in here, and that was 0.170 molar, and that would be our initial H3O plus concentration before this reaction goes through. And we do not know the concentration of PO43 minus, so we'll label that as X. And since H3O plus and PO43 minus are produced in a 1-to-1 ratio, we'll say 0.170 plus X, just that extra H3O plus produced by this third reaction. Although this X doesn't really matter, this plus X right here, and will be eventually crossed out later on, because the Ka3 for this reaction is so small that the x plus x here doesn't make a difference to that 0.170. It's just too small. The problem is, though, we do not know the concentration of HPO4 the initial concentration of that, and that we need to figure out the concentration of PO4 We need that initial HPO4 concentration. So how do we obtain this concentration of HPO4 that was produced by the second reaction that will be used up in the third reaction? Well, we have to go through the first reaction, the second reaction, to get the concentration of HPO4 So this is what we do. We know that in the first reaction, based on the previous problem, the first reaction produced 0.170 molar of H3O+. And therefore, it also produced 0.170 molar of H2PO4-. This is because the H3O+ and the H2PO4- are in a 1-to-1 ratio, so an equal concentration of both are produced. Now this H2PO4- is actually going to be used up in the second reaction because we can see it goes and gets used up here to produce this HPO4 whose concentration we're trying to find. So in the second reaction, in order to find the concentration of HPO4 produced by the second reaction, we need to draw the equilibrium equation for the second reaction. So the Ka2, which is 6.3 times 10 to the negative 8th, equals the product concentrations multiplied on top, so the H3O plus times the HPO4 H3O plus, HPO4 over the reactant concentration, which is H2PO4 right here. And in this case, we know that from the first reaction, we got 0.170 molar of H2PO4 that was used up here, so we can put this H2PO4 concentration to 0.170 molar right for this H2PO4 concentration. So 0.170 here on the bottom. And we do not put minus X right here, let's say, because frankly, so little of this H2PO4 is actually dissociated because this initial concentration of H2PO4 right here is 1.70, which is more than 100 times greater than the Ka2 for this second equation, which is very small, 6.3 times 10 to the negative 8th. So the minus x here on the bottom doesn't matter. And also we can put the concentration of H3O plus that is already present in the solution, and we know from the first reaction we got 0.170 molar of this H3O plus, and we can put this right here. And we do not need to put a plus x to this H3O plus concentration on top because, again, these other reactions contribute so little H3O plus that they make no difference. The H3O plus concentration essentially remains constant in the solution, like for all three. So it remains 0.170. And based on this, it becomes rather simple. We just cancel out the 0.170, 0.170, that equals 1. So x would equal 6.3 times 10 to the negative 8th. So 6.3 times 10 to the negative 8th molar of HPO4 is produced by the second reaction. Now that we know how much HPO4 is present in the solution, we can then figure out the concentration of PO4 that is produced. So again, we return to this Ka3 equation where we tried to find the HPO4 concentration on the bottom. We know now that it is 6.3 times 10 to the negative 8th. So the Ka3 equals the 0.170 plus x on the top, this H3O plus whatever was newly added by this reaction, times x, which was the concentration of PO4 over this concentration of HPO4 because HPO4 is a reactant. So it's 6.3 times 10 to the negative 8th minus x, whatever portion of it dissociated. And for every x of that HPO4 that's associated, we get an x of this and an x of this. So plus x and x. However, again, like for the other reactions, we don't need this plus x because the 0.170 molar H3O plus concentration remains essentially constant for all three reactions. So we just multiply 0.170 by x and we take out this plus x. And on the bottom, we do not need this minus x because the initial concentration of HPO4 which is 6.3 times 10 to the negative 8th, is more than 100 times greater than the Ka3 for this third reaction. The Ka3 is 7.1 times 10 to the negative 13th. That's 5 orders of magnitude greater. So little of this HPO4 dissociates that its concentration virtually remains constant. So we can just ignore this minus x and put the 6.3 times 10 to the negative 8th on the bottom. And now we can simply solve. We know that this Ka3 is 7.1 times 10 to the negative 13th, which equals 0.170x over 6.3 times 10 to the negative 8th. We just solve for x. And in the end, after solving this, we get the x to be 2.63 times 10 to the negative 18 molar of PO43 minus ion. So you can see that's very little of this ion is actually produced, but we needed to find how much at least is produced. So using some of our approximations and some of our strategies, we could find the PO43 minus concentration for this polyprotic acid, the anion concentration in the third reaction.